Welcome to all. In this video, we will see the calculations of stability of concrete dam in this video. Basically, stability is checked for three aspects. That is in sliding condition, overturning condition and stresses condition. Sliding condition able to help us to find whether dam is sliding horizontally or the dam is in not sliding. Whenever horizontal forces are more than friction forces, dam slides in horizontal direction. In overturning condition, we check resisting moments and overturning moments to see dam is not overturned as shown here. Further, we also check the stresses at various points at the base. This will help in identifying the places where tension is being developed or compressive stresses are more than the limits. Stability of concrete dam involves identifying different loads as shown here. Basic load is self-weight of dam. Then other important load is hydrostatic force of water and corresponding uplifts. Further, based on the shape of dam, upstream side weight of water can be considered if there is upstream slope. The important safety check in stability is consideration of earthquake forces. Earthquake forces of dam body shall be worked out. Also, reservoir imparts extra load onto the dam. This is known as hydrodynamic load. In this video, we will see computation of these loads one by one. After calculation of loads, the next comes is combination of load cases. Here we can see different load combinations for which we have to check the dam stability. These conditions represent various scenarios during the service life of dam. First condition is construction condition. That is, stability is ensured during or at the end of construction. Stability is checked not only at the interface of rock and concrete, but also if required stability checks need to be done at different levels. So in the construction condition, only weight of dam is considered. Similarly, the next condition is normal operation condition, that is, dams are built to store the water. That is, closing all the gates, dam owners able to retain the water in reservoir at full reservoir levels as per reservoir rule curves to meet the expected demands. Obviously, when the water is at full reservoir is more critical compared to water in reservoir at lower levels. The loads in this case will be calculation of weight of dam, calculation of water weight on the dam body due to dam body slope, uplift forces. Please refer to the foundation drainage gallery video in this channel to see the uplift reduction in the dam foundation. The same is explained again now. Dams have to store water is the main purpose. These dams are founded on different rocks. Some are very good and some are poor rocks. Concrete dams are generally placed on good rock. However, still there is a chance of seepage below the foundation. This seepage causes uplift pressure. Seepage depletes reservoir and also may cause erosion or piping problems. To stop the seepage and avoiding problems mentioned, we need to do the grouting in foundation. This is known as curtain grouting. This means forming a curtain up to required depth to stop the seepage. Further, grouting in the foundation may not provide the desired results. There still exists some seepage. To collect this seepage, drainage holes are provided and the seepage is collected in drainage gallery. As the seepage is collected, there is a reduction in seepage force or uplift force. Generally, this is assumed as reduction in 1/3 of full uplift at that drainage hole's location. If see the above uplift force diagram indicated in blue color, dotted blue line indicates reduction in uplift force. When the drainage holes are properly working, we have to consider the reduction in uplift force. When they are not working, we have to take the full uplift. After two load combinations, we have to check the stability in flood operating condition. That is when the incoming flood is there, gates are in open condition and water level in reservoir at maximum level, which maximum water level. This time, tailwater is also at high level or corresponding to floods, and uplift also we have to consider for upstream reservoir level, that is maximum water level, and downstream it is tailwater level. Earthquake loads also have to be considered as part of load combinations. Earthquake during construction condition and also dam normal operating condition shall be considered. To consider the earthquake loads, we need to have seismic coefficients as we are doing simple calculations. For detailed analysis in softwares, we might require time history and response spectra and so on. As these are simple calculations, we need to obtain horizontal and vertical coefficients. Every country has seismic maps which gives these value for different places. Otherwise, using various methods such as determining peak ground acceleration and other methods help us to estimate seismic coefficients. One more load combination is to check the stability in flood condition with full uplift. As already discussed, full uplift means drainage holes are not working. Here we will see the sliding stability formulas. By now, we know that sliding means when friction forces are less and horizontal forces, which are represented as shear forces in the above formula, are more, than there is a chance of sliding as shown above. To compute the factor of safety, which is denoted by Q, is derived using the formula. As concrete makes bond with foundation, there will be some cohesion force at the interface. Also the frictional resistance. These cohesion and friction values generally are determined at the site. Determination of these properties are important as they vary from rock to rock. Cohesion and friction values at the interface of dam body and foundation will be high for good rock and will be low for soft rocks. These are determined by casting concrete block of suitable dimension at the dam site on the foundation rock and shearing it to observe the cohesion value and friction value. Sometimes this is called as direct shear test at concrete to rock interface. As already discussed, signs of forces shall be considered accordingly. Uplift acts upwards, and weight of dam acts downwards. Uplift reduces the downward force. Using the above formula, for different load combinations we have to check whether desired factor of safety is obtained or not. For usual load combination, that is normal operation of dam, minimum factor of safety should be 3. Unusual is flood times, and sometimes we can consider construction conditions. Extreme conditions are earthquake condition at normal operation or flood condition with drains not working, that is full uplift in flood conditions. In some places, there is concept of using partial factor of safety instead of finding overall factor of safety. That is, partial factor of safety is included in cohesion and friction values. That is, cohesion is divided by partial factor corresponding to load condition and friction value also divided by respective partial factor accordingly. If we use partial factors in the formula, minimum factor of safety shall be 1. To account for the different load combinations, there will be different partial factors. Here we see overturning and stresses. Both are dependent, that is, we have to calculate moments about either A or about B, that is heel and toe. After working out individual load moments, equivalent vertical load and its eccentricity has to be worked out. This is shown in left bottom image. Eccentricity is shown as E in the image. We all know middle 1/3 rule. That is, if eccentricity falls out of the middle 1/3 region, there is chance of tension developing. The same technique applies here also. Maximum care has to be taken to restrict the eccentricity within the middle third. In some unusual or extreme load cases, little or minor tension is allowed and its limits vary from various standards as per applicable. Here eccentricity is towards toe, that is B side. At point B, compression will be more and at point A compression will be less, as we can see above image in blue color. Dam will try to overturn like this. Right side image again shown different loads to be considered, and generally stability we consider unit dimension if we see in the plan or horizontal cross section. All the loads in analysis is per unit width, either in meter or foot in out of plane direction. We can do for full block width also. Results are same as the cross section is same. Here we will see an example of doing dam stability. Whenever to start with stability analysis, we have to check the data completeness. Data include all dimensions, properties and all the parameters to be used in different formulae. Here for concrete dam we should check for total height, important levels of dam such as full reservoir level. Generally many concrete dams will be having upstream slope. In this example we are trying with upstream slope as vertical. From the slopes, the total bottom width can be worked out as shown for this problem. Regarding the data, concrete unit weight or density and water unit weight we have to collect before starting the problem. Further as discussed for sliding check, we also need to get the friction and cohesion at the interface of concrete to rock. This friction and cohesion values are to be obtained at field using direct shear test of concrete block casted on foundation rock. We are missing the gallery details to see whether any uplift reduction of full uplift. This we will consider in the next steps. First, as explained, is to check the data. We mostly have enough data. Let us start with analysis. First is to estimate weight. Then there are moments about either toe or heel. If you do about any point, the stresses will come same. For this problem, we will take moments about heel, that is point A. Dam body geometries are irregular depending on the complex shapes. For easy calculation, we have to divide into number of small or easy segments. Here we have divided the whole body into two parts, that is, one is rectangular portion and other is triangular portion. First is to estimate weight. Then there are moments about either toe or heel. If you do about any point, the stresses will come same. For this problem, we will take moments about heel, that is point A. Dam body geometries are irregular depending on the complex shapes. For easy calculation, we have to divide into number of small or easy segments. Here we have divided the whole body into two parts, that is, one is rectangular portion and other is triangular portion. Weight of first part is multiplication of width, height and density. As we have already discussed, the other dimension that is out of plane direction is unit, that is 1 meter. So all the calculations are per meter width of dam block. Weight of first part is 10 multiplied by 50 multiplied by density, that is 25. Similarly, we will get the weight for second part as per the triangle formula. Now we will enter the lever arm about point A. For first part it is half of width because it is rectangle. For the second part it is triangle plus width of first part. We all know for triangle center of gravity lies at 1/3 from the base. So the same are mentioned in the table. Now we have to multiply these lever arms with respective weights to get the moments about point A. After completing the weight and moments, then we have to work out stability in sliding and stresses. As already explained, the formula for sliding. Since the condition is construction condition, there are no horizontal forces. So the denominator in the formula is 0, hence there is no risk of sliding stability. Now we will see the stresses. We have already worked out and moments about heel, that is point A, as per the diagram. Total base width of our problem is 55 meters. Total vertical force, which is summation of first part and second part. Similarly, we calculate total moment. In the previous step, we have worked out lever arm and moment separately for different parts, that is first part and second part. Here, we have to see what is the combined or effective lever arm corresponding to total moment and total vertical force. Effective lever arm is obtained by dividing total moment with total lever arm. Here the value is 18.388. This is the distance from heel. However, base width is 55 meters. Center of base width is 27.5 meters. There is difference in effective lever arm and center of base width. This is known as eccentricity, which is shown as E here. So eccentricity worked out as 9.125. Just as a basic check to see whether tension will develop can be done by middle third rule. Total base width is divided into 3 parts. From center of base to either sides is base width divided by 6. So middle third is either side from center of base width lies up to distance of base width divided by 6. The eccentricity calculated is falling within the middle third, that is base width by 6 is greater than eccentricity, so there is no chance of developing tensile stress at the base of dam for this section. Stress calculation is done by the formula shown here corresponding to eccentricity and base width. Plus symbol means more stress, that is adding compression that is towards the point which we have taken moments about. In this case, it is heel, that is point A, so at A there will be more stresses and at B there will less stress, which can be seen from the above values after substituting the values in the formula. These values shall be checked with corresponding concrete strength as well as rock strength to compare. That is, if rock or concrete allowable strength is less than these stresses, then there will be problems to come, and accordingly we have to change the dimensions of dam section or propose suitable measures. We have seen construction condition. Now we will work out the stability for normal operating load condition. Normal operating condition means reservoir is at full reservoir level and uplift is normal uplift, that is, foundation drainage galleries are working properly. There is reduction in uplift at gallery location. First we will work out hydrostatic force. Formula for hydrostatic is half gamma head square. Head here is up to full reservoir level from foundation, that is 48 meters. Hydrostatic load acts at 1/3 of head from base, as it is triangular pattern load. Lever arm is calculated and accordingly moment due to hydrostatic force is calculated and entered the values here. Here we will work out uplift force acting on the dam. We have already discussed the function of foundation drainage gallery. These are generally placed at the bottom of the dam. The main purpose of these galleries to have inspection and also for collecting the seepage. Once the galleries are collecting seepage through drainage holes, the uplift pressure is reduced. Otherwise, there will be full uplift. The reduction in the uplift at the location of gallery is given in the above formula. There will be reduction in 1/3 of uplift due to galleries collecting seepage. In the formula, H- is denoting tail water level. The uplift at gallery is tail water head plus 1/3 of difference between reservoir head and tail water head. In our case, reservoir level is 48 meters. There is no tail water level in this condition, so H- is 0. Substituting this, we will get the uplift pressure value at the gallery location. Just like we have calculated weight of dam block by dividing into rectangles and triangles, uplift diagram also need to be separated for quick and easy calculations. Here the uplift diagram is divided into 3 parts. For each part we calculate uplift force, lever arm and corresponding moments. Force is calculated as area of diagram and lever arms are calculated as per geometries. In construction condition, there are no horizontal forces, so factor of safety in sliding was not calculated. But in this condition, there are reservoir hydrostatic loads. So using the sliding factor of safety formula, we can calculate factor of safety. First we will compile all the loads and their moments. Self-weight is the summation of 2 parts we have divided dam block into. Then hydrostatic load. Then uplift, we have split the load into 3 parts for convenience. Here area of section considered as base width of dam block multiplied by 1 meter, as explained already that out of the plane we are considering 1 meter thick of dam block. Substituting these values we get the factor of safety as 3.75. This is more than required, that is 3 for normal operation. Now we will see the stresses. This is again similar to the calculations we have done for construction condition. First we have to work out net vertical forces. Uplift is acting upwards, which reduces the self-weight. Hydrostatic force is not added in this as it acts in horizontal direction. Whereas, moments all are added as per direction. Self-weight and hydrostatic acts in clockwise direction about heel point A, uplift acts in anti-clockwise direction. So the total moment is sum of self-weight moment and hydrostatic moment and deduction of uplift moment. Once we have done this, the remaining steps are similar, that is finding out effective lever arm and checking whether the eccentricity is within the 1/3 of base or not. Using stress calculation formula, we can find out stress at heel and toe. Here also, eccentricity is within middle 1/3 of base, so tension is not developed, which we can see from the values of stresses also. Positive sign for stress means compression and negative sign of stress means tension. Now we will see the next loading combination. Flood operating condition is when the flood is passing through spillway. This time, as discussed already, if the spillway discharging capacity is less than the incoming flood, there will be rise in water level in reservoir. You can refer to the flood routing video of this channel where we have explained how to calculate the increase in water level. In this case we are considering that there is no increase in water level, that is spillway discharging capacity is sufficient to pass the incoming flood. So full reservoir level is equal to maximum water level. But during flood condition, there will be water in the downstream. This water level has to be worked out based on the downstream conditions. For this example, we are considering 5 meters of tail water level. In flood operating condition, the extra loads or different loads from normal loading are: one is upstream hydrostatic loading. If there is change in full reservoir level and maximum water level, then the extra hydrostatic load we have to consider. Similarly, the difference in tail water loads also we should consider. Uplift corresponding to variation of maximum water level and tail water level should also be considered. Here, there is no change in upstream water level. Upstream hydrostatic load is similar to normal loading condition. In the downstream, there is 5 meters of tail water. Water weight will act on the downstream slope as well as tail water hydrostatic force. Weight is calculated by area multiplied by water unit weight. In the triangle area, height is 5 meters, base or horizontal width is also 5 meters as the downstream face slope is 1 horizontal to 1 vertical. For this weight, we have to calculate lever arm and moment. Similarly, hydrostatic force also we have calculated and entered in the table along with lever arm and corresponding moment. We can see the difference in uplift diagram of normal operating condition wherein for this example, there is no tail water level. For flood condition, we are considering tail water level. We can see tail water head that H- contribution in uplift. Again, similar to previous uplift calculations, because of tailwater, we have to split the uplift into 4 parts for convenience. Accordingly, we have to work out the area multiplied by water unit weight, which gives uplift force, lever arm and respective moments. Here we see sliding factor of safety in flood operating condition. There is an increase in uplift. There is an addition of water weight at the downstream slope. In the horizontal direction, there is tail water hydrostatic force. Adding these changes in the formula, we are getting the factor of safety in sliding as 3.61, which is more than the required. As already explained, flood conditions are rare, so we can relax the criteria, that is, we are considering minimum factor of safety in sliding as 3, whereas in unusual condition we are considering as 2. Now we will see the stresses. This is again similar to the calculations we have done for previous condition. First, we have to work out net vertical forces. Uplift is acting upwards, which reduces the self-weight. Hydrostatic force is not added in this as it acts in horizontal direction. Whereas, moments all are added as per direction. Self-weight and hydrostatic acts in clockwise direction about heel point A. Uplift acts in anti-clockwise direction. Tail water hydrostatic also acts in anti-clockwise direction. So the total moment is sum of self-weight moment including water weight and hydrostatic moment and deduction of uplift moment and deduction of tail water hydrostatic load. Once we have done this, the remaining steps are similar, that is, finding out effective lever arm and checking whether the eccentricity is within the 1/3 of base or not. Using stress calculation formula, we can find out stress at heel and toe. Here also, eccentricity is within middle 1/3 of base, so tension is not developed, which we can see from the values of stresses also. Now let us see the one of the extreme case, that is during the flood condition, drainage holes are not working properly, that is, they are choked, so uplift is not reducing as per the planned. This we can see in the uplift drawing. Earlier there is reduction at the gallery. Now we can see the dotted line indicating increase in uplift pressure. We will do the stability check for this loading condition. We can see the difference in uplift diagram of normal operating condition, wherein for this example, there is no tail water level. For flood condition, we are considering tail water level. We can see tail water head that H- contribution in uplift. Again, similar to previous uplift calculations, because of tailwater, we have to split the uplift into 4 parts for convenience. Accordingly, we have to work out the area multiplied by water unit weight, which gives uplift force, lever arm and respective moments. Here we see sliding factor of safety in flood with extreme uplift condition. There is an increase in uplift. There is an addition of water weight at the downstream slope. In the horizontal direction, there is tailwater hydrostatic force. Adding these changes in the formula, we are getting the factor of safety in sliding as 3.02, which is more than the required. As already explained, extreme conditions are rare, so we can relax the criteria, that is, we are considering minimum factor of safety in sliding as 3, whereas in extreme condition we are considering as 1. Now we will see the stresses. This is again similar to the calculations we have done for previous condition. First we have to work out net vertical forces. Moments all are added as per direction. Self-weight and hydrostatic acts in clockwise direction about heel point A. Uplift acts in anti-clockwise direction. Tailwater hydrostatic also acts in anti-clockwise direction. So the total moment is sum of self-weight moment including water weight and hydrostatic moment and deduction of uplift moment and deduction of tailwater hydrostatic load. Once we have done this, the remaining steps are similar, that is, finding out effective lever arm and checking whether the eccentricity is within the 1/3 of base or not. Using stress calculation formula, we can find out stress at heel and toe. Here also, eccentricity is within middle 1/3 of base, so tension is not developed, which we can see from the values of stresses also. Till now we have seen general load combinations. Now we will see load combination involving earthquake. Seismic coefficients are denoted by alpha. It is assumed that the variation of seismic coefficient with height varies in triangular portion, with 0 at bottom and maximum at top. Depending on the respective country standards, these coefficients are multiplied by factors such as 1.5 or 2 times to incorporate safety. Here in our problem we are directly taking seismic coefficients without any factor. For example, force is multiplication of mass with acceleration. We have seismic coefficients as accelerations. We have to multiply them with mass. As we can see here, seismic coefficient is varying with height and also mass for different parts. Same like weight calculations, these can be calculated by dividing into parts. For varying acceleration values, for different shapes we can find out the force and respective lever arm about point A. We have rectangle and triangle blocks only in our problem. For these, horizontal and vertical earthquake force and lever arms are shown here. In the previous step, we have seen the formulae for force and lever arm. In this step we will work out for our problem. As already explained, seismic coefficient varies with height. Our example has 2 parts. First part is up to full height. Second part, that is triangular part, is up to 45 meters only. Accordingly, we have to calculate seismic coefficient maximum for part 2. Dotted line shown on the left side variation. Same has been calculated for part 2. You can see the variation. We have already worked out weights for first part and second part. Using them, geometry details, we can work out force, lever arm and moments as shown here. In construction condition, there are no horizontal forces, so factor of safety in sliding was not calculated. But in this condition, there is horizontal earthquake. Vertical earthquake reduces the weight, so it is deducted, and denominator we have used the value of horizontal earthquake. As there are no other loads, the factor of safety in sliding is much higher. There are 4 combinations possible for earthquakes, such as horizontal downstream, vertical downwards, horizontal upstream, vertical upstream, like this. We have to select the critical among 4. If needed, all the 4 cases values to be noted and calculations are to be done. In this example, critical combination is presented in all the earthquake combinations. As calculated for other load combinations, stress calculation is done by the formula shown here corresponding to eccentricity and base width. Along with self-weight, horizontal earthquake loads and vertical earthquake loads along with their moments are noted here. Following the same method, estimation of eccentricity and using the formula, stresses at heel and toe are estimated. As the eccentricity is within 1/3 of the base, there is no tension at the base of the dam in this case. We will see the final load combination, that is normal operating load case with earthquake. Already we have worked out normal loading condition. All the loads, lever arms and moments are same for this condition also. Only change is addition of earthquake loads and hydrodynamic load. In the previous load condition, we have calculated horizontal and vertical earthquake loads. We will have to work out hydrodynamic load. Its variation from bottom to top follows like this. Here we discuss the method to estimate the hydrodynamic load. Hydrodynamic pressure is calculated by the formula given here. Pressure is equal to multiplication of C, alpha, unit weight and H from reservoir level. The coefficient C is estimated from the graphs given here. C is dependent on Cm, which is maximum value from the graph. Here the slope is vertical for this, it is 0.735. At the base of the dam, Y is equal to H, then from the formula C is also equal to 0.735. Using this, hydrodynamic pressure is calculated. This method also describes horizontal force and moment. As shown here, we calculate the hydrodynamic force and moment, which we will use for calculation of sliding factor of safety and stresses. Here now we see the sliding factor of safety for this load combination. Here the vertical forces are deducted by uplift force and vertical earthquake force. Horizontal force, which is hydrostatic force, is added by horizontal earthquake force and hydrodynamic force. The factor of safety in sliding is obtained as 2.49. In the stress calculations which we have done for previous load combinations, moments in clockwise are added and anti-clockwise are subtracted. The effective lever arm is 29.03. Eccentricity is negative, this means it is other side of center of base. Eccentricity is towards toe side, so there will be more pressure towards toe side. This condition also, there is no tension at the bottom of the dam base. We have worked out the stability for all the conditions shown here. Out of 6 conditions, tension is being developed at toe in construction with earthquake loading condition. As this is rare and as per the respective standards, tension limits have to prescribed. Sliding factor of safety decreased from normal operating case to normal operating case with earthquake. Overturning stability can be worked out for all the conditions as the ratio of resisting moments to overturning moments. That is in this case ratio of sum of all clockwise moments to anti-clockwise moments. Once the summary like this prepared, it is easy to identify the critical condition. Also, further optimization in dam geometry can also be done if the values or limits allow. Hope the calculations are easy and helpful. Thank you.